Hi, everybody, and welcome to another recorded Zoom interview. Look who we have here. It's an old friend.
Morning, Nick.
University of Puget Sound geology professor emeritus, Jeff Tepper. I think we did 7 or 8 of these last winter with the Cascade series. Jeff, what's the weather like this morning in Tacoma, Washington?
Dismal.
Okay.
There's a lot of fall color. It's just all lying on the ground.
Yeah,
So,
sounds familiar. About the same here. Well, viewers, can I talk directly to you for just a second? In the Alaska series so far, this November of 2025, we've been talking about the work of Bob Hildebrand. And there is a paper by Hildebrand, 2018, written by Bob, Joe Whalen, and Sam Bowering, resolving the crustal composition paradox by 3.8 billion years of slab failure magmatism. And that's really what we want to talk about today with Jeff. I thought it would be important for us to go to Jeff, who has a lot of experience as an igneous petrologist, teaching for a long career, and publishing on arc magmatism and slab failure magmatism in the Cascades primarily. But I need to hear from Jeff right now, and I don't know what he's going to say, but I asked Jeff if he wouldn't mind spending some time with that 2018 paper by Hildebrand, and we just kind of react to what Jeff wants to say about what he thinks. Do you have some opening comments? What was that paper new to you, Jeff? And what's your initial reaction to? What's the headline, I guess, from your reaction to the
okay.
paper?
I like the paper. Um, I was familiar with Bob's basic ideas of slab failure magmatism.
Mm-hmm.
What I did not appreciate was partly how grounded it is in like regional geology,
Right.
and then secondly, how the conclusions that come from the idea of slab failure magnetism actually pertain to these other seemingly at first unrelated issues, like how do we make continental crust in general.
Mm-hmm.
But when you fit them together, I mean, that to me is sort of a compelling angle on this. It's seems not just fortuitous when one model has implications for another model and sort of answers some questions. So I like the paper overall. What I was thinking I would talk about is
Yes.
not necessarily the broadest implications of it,
Right.
but just how this process relates to your A to Z Alaska, with a little other broader implications, and a little bit about how I see this. Um, how well does this explain what I saw in northeastern Washington, which we talked about some last winter?
Well, let's do a little bit more of that verbally, and then we'll go to your slides. So, can you remind the viewers what we were doing last winter, and what experience do you have with "quote unquote" slab failure magmas versus arc magmas here in the state of Washington?
Sure. So we were, I guess we'd say we were sort of setting the stage for talking about the Cascade Arc,
Yes,
and that required thinking about what was happening in the Cascadia region before the arc turned on.
before the arc turned on.
And so one of the major events that happened immediately before the arc turned on was the arrival of Silesia.
Yes,
And then one of the consequences of the arrival of Silesia, which was moving toward North America, riding on an oceanic plate, but when Silesia arrived and was an unsubductible buoyant mass, subduction was terminated and that plate had to break off.
hmm.
So that break off, is very much like what Bob's talking about when he talks about slab failure magnetism. And what we talked about last winter was what is the geologic evidence for that in the Northwest. And it was primarily this sweep of igneous activity, which started about 52 million years ago in Idaho, and then progressed southwestward across northeastern Washington, culminating about 46 million years ago.
Yeah,
Sorry, my clock is
you're fine.
chiming.
Oh, yeah, Mr. Clock. That's right. Yeah. So
Yeah.
so you were calling those slab failure magmas
Well,
literally.
I was calling it slab rollback.
Okay.
So I wasn't using the term slab failure, but I think there are a lot of similarities.
Sure. Let's
In
try
both
one.
cases. Okay, go ahead.
Let's try one. I'm sorry to cut you off. Let's try one more, because to me, I stumbled into this question in the last episode recently, and I wonder what your perspective is on it. A couple generations ago, do you think the worldwide geological community, once plate tectonics was established, assumed that every major batholith or pluton was arc generated? And that in the last 20 years or 30 years, including your work, have we been re-examining that assumption that everything is related to an arc, and then suddenly we're finding more and more non-arc related magmas?
I don't think every granite was assumed to be part of an arc,
Okay.
because there are, for example, a lot of granites in the mid-continent which are nowhere near a subduction zone.
Okay.
And as far as we know, never were.
Right.
So there's a mid-continent rift, but there's no evidence that was mid-continent subduction zone.
Okay.
So not all granites were attributed to subduction, but also not all granites look the same. So
Sure.
as early as, in the 70s, a distinction was made by some Australian geologists between what they called I-type granites, which meant igneous source. And those are the things that you see in an arc setting.
Mm-hmm.
So BADR, but in
Right.
basalt, andesite, dacite, rhyolite, but in the
Right.
plutonic equivalent. And those were very different from these rift-related things,
Yeah.
which got the designation A-type granite, meaning anorogenic, but also meant anhydrous and alkaline. So they were just very different. So I think it would be safe to say that most geologists, when thinking about granitic rocks emplaced along a continental margin, a
Right.
convergent margin,
Right.
thought those were arc
Okay.
magmas, but not things that were in other tectonic settings.
Fair enough. So we're closer to the margin. We're assuming a generation or two ago that most of them, maybe all of them, are related to a subducting plate somehow. And then I think
Right.
of my case of being a graduate student in Idaho. We've already gone through this last summer, but we were calling it the Idaho or the Chalice Arc in Idaho.
Right.
Everyone assuming and writing, the experts saying there's subduction somehow to create the Idaho batholith. And then we discovered a year plus ago that that's for sure not the case. And we wouldn't want to call those slab-failure magmas, though, necessarily, with the Idaho batholith.
No, I don't think so.
There's
But the idea, once the idea of terrain accretion came into being, and people accepted that the continent's margin wasn't always where it was, then you could argue that, well, Idaho was actually not that far from the margin,
Right.
so it could be an arc.
Right, right. Okay, well, that's the context. I know we're not going there in just a second when we get to your slides, but to me, that's where I'm coming from. I guess I'm talking mostly to the viewers. Like, why are we doing this deep dive into geochemistry with magmas? It seems like this question is going to be with us all winter, especially when we get up to Alaska. And my simple-minded thought at the moment is every time I go to a pluton or a batholith in Alaska, I'm going to try to use some tools that I've learned from you and Bob and others and really try to investigate that we have arc or not. We got another clock going? What the hell's going on now?
I just got to silence my phone. Sorry. I don't know as much technology as you, but I'm just not as good at it.
Okay. Well, thank you. Jeff Tepper, would you please share your screen? I think that's plenty of backstory, and you have such a nice connection with our viewers that I'm sure everyone's going to be excited to see you again. There we go. We've got a full screen, and please, I'll interrupt you once in a while, but otherwise, let's see what you've got. Thank you.
Okay. Well, so I thought we would look at sort of the geochemical evidence that supports this idea that there are two processes that are making granitic rocks at a convergent margin.
Thank you.
And I think one of the things that is cool that I'll come back to is, this is Half Dome, one of the most famous granites in the world, Yosemite Valley.
Mm-hmm.
And it has been interpreted many different ways in the last 50 years. And I think each time there's some new thinking and some new analytical tools, we get a new perspective. So I think that the fact that the slab failure magmatism involves one of the best studied granites in the world is significant.
Thank you.
Okay, let's see. All right, so I thought we should start off just demystifying a little bit some of the geochemical diagrams that get used to just differentiate slab failure magmas from other types.
Mm-hmm.
So we'll talk about two minerals that are important in this story. So one of them is plagioclase feldspar, and it has the formula shown here, calcium aluminum silicate. And like any mineral, it has a structure. It's crystalline. So this little cartoon up in the upper left is the crystal structure of plagioclase. And so each element, each ion has a place in that structure.
Hmm.
And so it fits in a little, we'll call it a site, a crystallographic site. And so uh, each different ion, which has a different size, is going to fit into a different site.
Okay.
So in order to be plagioclase, you always have to have calcium, aluminum, silicon, and oxygen. If you don't have those elements in those proportions, it's not plagioclase.
Mm-hmm.
But it doesn't have to be pure. So you can substitute in other elements if they fit into the same site, if they have the appropriate size. And those are called trace elements.
Mm-hmm.
And so in the case of plagioclase, the element strontium has the same charge, and it also has a reasonably similar atomic radius. So this A with a little O is an angstrom. That's 10 to the minus 10 meters. So that's the unit we would use to talk about the size of ions. So because calcium and strontium have the same charge and the radius is within about 15%, strontium can take the place of calcium in that mineral.
Mm-hmm.
And so we say, therefore, that strontium is compatible, which means it's welcome into the crystal structure. And in terms of thinking about melting, then, if you have a magma and you have plagioclase in it, strontium would prefer to be in the crystal where it's compatible as opposed to the melt.
Mm.
Let's contrast that with the element yttrium, which does not have a 2 plus charge. And even more disturbing to the plagioclase crystal is that this ion has a smaller radius. And one thing nature doesn't like is an ion that's rattling around inside the crystal. So if it's okay to be a little bit bigger,
Yeah.
all right, so then the crystal structure will stretch a little bit,
Yeah.
but you can't shrink it. So yttrium being a little too small and having the wrong charge is not welcome in plagioclase to make
Mm-hmm.
this sort of anthropomorphic.
Mm-hmm.
So we say it's incompatible. And therefore, if you have a plagioclase crystal in a melt, yttrium would rather be in the melt.
Mm.
So that means that if you have a melt that's coexisting with plagioclase, it's going to tend to have low strontium because the strontium's in the plagioclase,
Mm-hmm.
but high yttrium because it's in the melt. All right, so far so good.
So far, so good. Like, this is the background that I think all 99% of the geologists need when they look at these discrimination plots that are put up in a geochemistry talk.
Okay, so then let's contrast that with garnet, which
Mm-hmm.
has a different chemical formula.
Thank you.
And we don't need to go all through all the details, but because of size and charge,
Yes.
strontium is not compatible in garnet,
Okay.
but yttrium is. So we have the exact opposite situation. If
Yes.
you have a melt coexisting with garnet, the strontium would rather be in the melt, but in the yttrium would rather be in the crystal. So that melt will have high concentration of strontium, but low yttrium because the yttrium is left behind in the crystal.
Okay. With you so
Okay.
far.
Okay, there's one other group of elements we want to introduce that follows basically the same rules, and that's the lanthanides,
Mm-hmm.
which are also known as rare earth elements. And they're the ones that sit down here in a row below the rest of the periodic table. And that's because um, they are formed by adding inner orbital electrons. And so they all have the same charge, except for the element europium, which we'll talk about, which has a +2. All the rest are +3.
Okay.
But as you go from lanthanum to lutetium, the ionic radii gets progressively a little bit smaller. And that's going to affect then the compatibility.
Mm.
So we'll go back to the same two minerals we were thinking about before, which is
Mm-hmm.
plagioclase and garnet.
Mm-hmm.
So on this diagram, this is the concentration of the mineral of the element divided by the liquid. So
Okay.
if you're above 1, there's more in the mineral than in the liquid. That's a compatible element. So anything up here is compatible, down here is incompatible. And this is on a log scale. So it's if the element plots down here, it is really unwelcome.
Really incompatible, yes.
But up here, it's a love affair.
Mm.
All right. So if we look at plagioclase, in general, rare earth elements are excluded, with the exception of europium. So if you were to melt a rock, let's say the rock started off with the concentration just given by that purple line,
Yes.
and you melt a rock and you leave behind plagioclase and make a magma, the magma must be the inverse of this. So it would have a higher concentration of rare earth elements, but a depletion in europium, which was left behind.
Okay.
Because you have to be able to put the melt plus what's left behind back together to get what you started with.
Mm-hmm.
All right, so in general, then, if you've left plagioclase behind during the melting process, you'll have a fairly flat rare earth pattern across from light to heavy, but you'll tend to have a negative europium anomaly.
Okay.
Garnet is a very different fingerprint. So garnet is this line here, and garnet does not accept the lighter rare earths,
Right.
but it really likes the heavy ones,
Mm-hmm.
and it doesn't care at all about europium.
Okay.
So if garnet is present when you melt and you produce a magma, that magma will be enriched in the light rare earth elements, but depleted in the heavy ones. And so you'll wind up with a steep slope, a steep negative slope in terms of these elements on a diagram like this. And that's often described as a high lanthanum to ytterbium ratio, because lanthanum's over here and ytterbium's over here.
I'm chuckling because if you were anybody else, I'd be nervous right now. Like, good Lord, this is never going to go anywhere. But it's you, and I have 100% faith in you that this is going to pay off.
Okay, we've done all the heavy lifting. Okay? All right. Are we okay?
Yes, we are. That was my way of saying we're okay.
All right. So then let's ask the question, why do we pick plagioclase and garnet as the two minerals to talk about?
Beautiful.
And the reason is, if we think about a subducting plate, or the subducting crust in the plate, it's basalt. And so at the time it formed on the sea floor, basalt has a lot of plagioclase in it. So it's a plagioclase and pyroxene rock.
Mm-hmm.
But as you take that subducting plate deeper into the mantle, when you get to a depth somewhere 40 or 50 kilometers, the basalt transitions into a denser rock called eclogite.
Mm-hmm.
And that's a rock composed of garnet and pyroxene.
Mm-hmm.
Right here. That's this. All right. So, and the plagioclase is gone.
Yes.
So if we were to melt the subducting plate, or basalt in general, if it's basalt, we're leaving behind plagioclase in the residue.
Mm-hmm.
But if we're melting it down here deep, we're going to leave garnet in the residue.
I gotcha.
All right, so what the trace elements are telling us here, these two, we're going to use these two ratios, the strontium-yttrium ratio and the lanthanum-ytterbium ratio.
Mm-hmm.
This is worse than tantalum, niobium, and all the things we talked about. But you're getting a tour of the periodic table.
No, this is great. This is
great.
So
it's about depth of melting.
Yes.
Okay. All right, so here's a paper, a figure out of Bob's paper.
Right.
These are data from the Peninsular Ranges batholith in Southern California.
Okay.
Here are the two ratios we've talked about.
Right.
So when lanthanum-ytterbium is low and strontium-yttrium is low, that says plagioclase left behind.
Mm-hmm.
And when lanthanum-ytterbium is high and strontium-ytterbium is high, that says garnet was left behind. And so this says shallow, melting shallow, and this says melting deep.
Good.
And the intriguing observation here was that that difference in depth of melting corresponded to the ages of the plutons.
Yes.
So the older plutons, which are labeled arc here and look like arc magmas in general, were forming coming from a shallower depth than the ones that happened afterwards.
Can you stop your share for a second?
Yeah.
Let's just try a couple things here. Great job. I knew we were going somewhere. I wasn't exactly sure where, but that's where we went. And so I assume there's more with more plots and fleshing things out a little bit more. But maybe we're catching our breath, and I'm just wondering, has that logic and those trace elements been used in Washington State by you or others to distinguish this story?
So one of the things that is important to keep in mind is that this ratio, these element ratios, they tell you whether there's garnet or plagioclase involved. They don't tell you whether it's slab melting or deep crust melting or something else. So you have to, I think one of the things that I liked about Bob's paper, and that I think is true for geology in general, is you need to integrate multiple lines of evidence before you come up with a model. And so
you read my mind. That's where I wanted to go next. But please continue your sentence there.
So these trace elements are an important tool, but if you don't use anything else, they're not very definitive, I would say.
So I don't know. This might be a dead end, but let's try it. Like if we've got a tool belt and we want a bunch of tools in our belt ready to attack this problem, we show up at Mount Stewart or wherever. One are the two elements we were just looking for, the two minerals, garnet and plagioclase, or more accurately, those trace element ratios you were just showing us.
Right.
Are there a half a dozen different trace element ratios plus mafic enclaves and other kind of outcrop type things? What else can we have in our tool belt without giving away the rest of your slides?
Okay, so there are other trace element ratios.
Okay.
Different ratios tell you different things. So these ratios are telling you something about what minerals were in the source, which is also telling us about depth.
Okay.
Then there are other ratios which we used some last semester, last alphabet, that tell you something about tectonic setting.
Yes.
So we were, your favorite boron-beryllium ratio.
It is. Yes.
That's telling you something about fluids.
Okay.
So the criticism I would make of some geochemists is they don't explain very well why these ratios work.
Mm-hmm.
But they are based on either experimental data or field observations.
Yes.
So there's a lot of work that goes into establishing what ratios are useful for what questions.
And then correct me if... Go on, I'm sorry, go ahead.
But to finish your original question,
Yeah.
so trace elements are one tool.
Yeah.
Isotope analyses are a second tool.
Okay.
Geochronology is an important tool. I mean, I'll say something about this later on,
Good.
but you have to know something about the ages, relative ages of the rocks you're talking about, because if they're super different in age, no matter what the chemistry says, they're probably not related to each other.
Right.
And then there's the field relations, which were an important part of the slab failure story, I think.
Well, that's the last thing I want to say before we go back to the slides. It feels, without knowing anything, it feels like it's rare to have someone, like most things in geology, it's rare to have somebody who's like a Renaissance person who can deal with all these field geology, comfortable in the lab, bringing in something else and making it all work coherently. I mean, I'm complimenting you, I guess. I know you're out in the field banging on rocks. I don't know if you're mapping necessarily, but does it feel like there's a lot of geochemists who can also use all these tools and put it all together in a mapping project?
I think there are, but I think there's also collaboration.
Yeah.
So a person who's a lot of lab work needs to be, lab work in general needs to be grounded on where your samples came from.
Yes.
So if you didn't collect the samples, hopefully you're relying on somebody else who did, who is very familiar with the geologic context, because otherwise sort of analyzing something that's just floating in space.
Yes, yes. Okay, well, this is just what I was hoping for, Jeff. Thank you so
Okay.
much. Let's return to your slides, and I'll be along for the ride for the next few minutes. Magma right there.
Okay, so back to the slide we were in.
Yes.
All right, so again, so this is the Peninsular Ranges, Southern California. This is one of the key localities where Bob and Joe Whalen tested their model.
Mm-hmm.
All right, so one of the reasons I particularly liked their paper was because it focused on the Peninsula Ranges. And the Peninsula Range, so a paper came out about the Peninsula Ranges in 1987 by Gramet and Silver. That was like the year I started my PhD.
Nice.
And I read this paper over and over again, and it was incredibly, still is very influential in my thinking, but not for the reason that has anything to do with slab failure.
Okay.
So I'll just show you what Gramet and Silver observed. So the batholiths down here in Southern California, and they observed that there were three belts geochemically different belts in that batholith, which are western, central, and eastern. This ratio here, we didn't talk about these elements. This is the same as lanthanum deuterbium. This is that rare earth ratio.
Okay.
These are also rare earths. They just shows different ones. But again, the bigger this number is, the steeper the slope would be, the more garnet flavored your source was. So what they observed was that these three belts had different rare earth patterns, basically, and different amounts of strontium. So those belts, their boundary lines are here. So the western belt was over here, the central belt was here, and the eastern belt was here. And what was important to me about this was that you cannot get from one of these to the other by fractional crystallization. So, a big question is today, still probably, but maybe less so, is are granites the result of partial melting and then not much modified on the way through the crust to the surface? Or are they the result of extensive fractional crystallization? So there's both of those processes can produce a felsic silicic liquid.
Right.
But they're not the same process.
Yes.
So this, to me, was the first time I saw a really compelling, irrefutable, I would say, argument that granites, at least in the Peninsula Ranges, are showing you something about the minerals in their source.
Wow.
And
Nice.
so they recognized that these rocks over here with the garnet must be coming from deeper down. So this was their model. And that the rocks in the west that had the shallower melting were part of a volcanic arc. And that source was somewhere like 30 kilometers below the surface. They're melting something at the bottom of the arc.
Okay.
But it's not deep enough to have garnet. It's not epigite.
Yes.
And then over here farther east, well, here's the source of those rocks with the garnet. It's kind of ambiguous as to what this is doing down here. And hiding in the corner, but here's the subducting slab. But in the 1980s, nobody thought that subducting slab could melt. So that idea didn't really show up until 1990.
Okay.
So rather than invoke melting of the slab, which was deemed to be impossible because the slab is too cold, Gramet and Silver have this eastern, deeper source region. And I didn't reread the paper carefully, so I don't remember what their interpretation of this was, but it wasn't melting of the slab. All right, so these data, shallower melting on the west, deeper melting in the east, this is going to sound a whole lot like the slab failure story.
Yeah.
It's just at this point, they didn't think the slab was part of it.
Got it.
All right, so then Bob and Joe, this is a figure from the 2018 paper.
Yes.
Made an additional observation that I think was quite fundamental, which was that, so this again is, let's see, here we are in over here, these are the arc rocks. So this is west, this is east,
Yes.
and this is age. So the older stuff, which is also the stuff farther west, has the arc-like signature that has the shallower melting. The stuff to the east, younger and deeper. But in between those two, there's this deformation event, which I don't remember reading about in Grammet and Silver, but may well have been there.
Mm-hmm.
So this is just the same diagram we saw before,
Yeah.
but between this time period of these older arc rocks and these younger failure rocks, there's some kind of a deformation event.
Mm-hmm.
And so the story then was that that deformation event was a terrain collision, which has caused the slab to break off. So the slab failure model is that you have a convergent boundary and there's an arc, but then you have a terrain or something sitting on the subducting oceanic plate, which is unsubductible. So it collides, then the slab breaks off. This is eclogite down here. This melts, so I put this arrow in to show that this melting of this produces these diagnostic high strontium, high lanthanum ytterbium magmas that have garnet and source. That, by the way, is exactly the same signature as an adakite.
Okay, I was just going to bring that up. Yes.
Yeah, so um, you could use, to me, you could use adakite and slab failure magmatism as sort of synonymous,
Mm-hmm.
although there are differences.
Okay.
Okay, then not so well shown on this diagram, but important. Sorry, if I had turned it off.
Okay.
Is that as this slab melt ascends toward the surface, it's going to interact with the mantle. And so it's going to be modified in terms of composition. And that doesn't have a profound effect on its trace element ratios. It might affect the abundance of trace elements, but the ratio stays about the same. So that slab melt signature is intact. However, the isotope composition of that could be affected more significantly.
Okay, I'm starting to lose it. So
Okay.
stay with this slide.
Yep.
In the upper diagram,
Yes.
we have an arc set up.
It doesn't really show the arc, but the volcanoes would be sitting here.
There, that's what I was going to ask. So we're generating magmas in the mantle wedge above the subducting slab. We're doing the BADR. We're doing normal volcanic arc stuff. And if you're a rookie still with this program, congratulations, number one, for staying in here. Number two, we're tying a subducting slab with a volcanic arc. Those two concepts go together. Arc magmas mean we have a subducting slab going down a trench. Okay.
Let me
go ahead, please.
I was going to say, maybe to annotate this a little better.
Yeah.
In this stage here, where we're just subducting the oceanic plate the normal way,
right,
it's giving off water,
mm-hmm.
and that's causing melting here in the mantle wedge.
Yes.
But the slab's not melting.
Okay. And then we go to the bottom diagram. We're saying we're generating, that's the topic of this video program, we're generating non-arc magmas. I'm thinking only because of the tear in the slab, what I've learned from you last winter, but you're saying it's not just that?
So maybe this wasn't the best choice of diagram.
It's okay.
For a couple of reasons. One, it doesn't show the arc, so we tried to add that verbally.
Right. Yeah.
And it's showing that the cause of break-off melting is simply asthenosphere coming up through this tear.
Which is the only way I know how to visualize it until right now.
Okay.
You're gonna give me a different visual, I think.
Okay, so I think that happens, and I think that happened in Western Washington, but that's a little different because that's not melting the slab.
Right.
That's allowing the mantle to come through here,
right,
and then decompress and melt.
Good.
The slab failure story is that we're melting this blue stuff here, the crustal part of the subducting plate is melting.
Okay.
That's producing a felsic melt, kind of an adakite-like thing.
Yes.
As that melt rises through the mantle, it's going to interact with the mantle.
Okay.
And that interaction is going to show up in isotopes more than in elements.
I see. So
And so,
so thinking back to the first couple slides of your program, we don't need to go back there, but our periodic table and those elements and the two minerals, those signatures that you established early in this little slide deck, that's from the tear?
no,
More
that is from the
it
melting
is.
here.
Okay.
Yeah. And
Okay.
so that the I guess an important point is that that signature will be intact even after this magma has interacted with the mantle or
Okay.
the crust on the way to the surface.
Right. Okay. Okay.
Okay.
One more. I'm sorry. Just one more
No,
while we're
no.
here. Um, I did an episode yesterday or 2 days ago, and people were confused about where the slab failure magmas. Why are you getting slab failure magmas to the east of the arc? Uh,
Okay,
that's
let's not
coming probably, right?
let's sort of coming.
Good.
So
Okay. I think I see it here for the first time. You do have, if we're visualizing where the arc was, the arc is to the west in this east-west cross section of the slab failure magmas.
so in this cartoon, the arc would have been, somewhere here,
Oh,
and
okay.
these things are coming up behind the arc because the slab has gotten deeper.
Oh, okay.
So this is a generic Wikipedia cartoon. It's not
Yeah, right,
intended to be
right,
Western North America
right,
necessarily.
right. Okay.
But let's just say
Yeah.
this one more time. So there was an arc in this up in here. There would have been an arc,
Yes.
and it was the product of dehydration of the subducting plate causing melting in the mantle wedge,
Mm-hmm.
and then typical arc magmatism.
Mm-hmm.
But if you proceed farther away from the trench, where the slab was deeper,
Hmm.
after subduction was terminated by some sort of an accretion event, and the slab broke off, then that slab began melting. It produced this high lanthanum ytterbium, high strontium yttrium garnet in the source melted eclogite.
Yes.
That material is then going to become the slab failure granites that pop up
To the west of the arc magmas.
in this cartoon. Yes.
Okay. All right. Well, that's a
I
crucial
mean,
part that I need to keep
yeah. All
working
right.
on
And
with Bob. I guess it's not your
yeah,
job to
because
do that, but
I can't answer that
right.
because I don't understand that
Yeah.
either. I put a
Okay.
slide in about that. But
That's good. Okay. Good. I don't want to
okay.
hold you up. Let's keep
All
rolling.
right. Last point.
Yeah.
So these magmas on the way to the surface can have their oxygen isotope modified. And we don't need to belabor the details, but mantle oxygen coming out of the mantle has a value of about 6.
Hmm.
So we call it delta O18, about 6 per mil.
Mm-hmm.
And going through the mantle may also affect the strontium isotope
Hmm.
composition. Now, normally I've always thought, when that ratio is high, that tells you there's continental crust involved.
Mm-hmm.
An unhelpful aspect of Mother Nature in this case is that in some cases the mantle can have high 87,
Oh,
86 strontium as well. That's super unhelpful,
right.
but we don't get to choose that.
No, I guess not.
So I just said it varies widely depending upon basically whether that mantle has been modified by earlier subduction.
Okay. Very good.
Okay, so this is just a cartoon of all these
Yeah.
batholithic belts,
Yeah.
and I think Bob has made the case that many of them, particularly the Sierra Nevada and the Coast Range, have this signature of the slab failure story. And this, is a table that comes out of one of their papers, and I just put this in to point out that the claim that this is a slab failure story is not solely based on isotopes and trace elements. There's
Right.
all these other questions. Do we have the appropriate other geologic components of a collisional story? And I'm going to immediately say I'm not familiar with the regional geology of this, so
Who
I
is
can't.
except him?
Well,
Yeah.
right.
Right.
But yeah, I mean, the Cascades here, and this is a different part of the Cascades than I've worked in,
Right.
but these are rocks that Bob Miller and others have worked on, so they would be a better person to ask how this fits the failure story.
And
So
yet,
I don't want to belabor this, but anyway, yeah, go ahead.
well, I just have one question before we lose this map on the left margin. I think Hildebrand, correct me if I'm wrong, but I think Hildebrand and Joe are saying more than 50% of the magmatic stuff in those red blotches are slab failure and not volcanic arc. A,
Right.
do you think that's what they're saying in the paper? And B, does that really shake you up or does that seem reasonable?
I don't remember a percentage, but I think that their
It's not
data
trivial amounts.
would say it's a significant,
Yeah.
maybe 50%, maybe more.
Yeah.
Um, I circled this area here because that's the area that I know something about.
Sure.
So I'm going to then ask the question, do those rocks fit into the slab failure story?
Okay. Yeah, here we go.
All right. So this is, citizens of the Z Nation saw this map last year. And the point was, so there's British Columbia, here's the Idaho-Washington border. So we're looking at northeastern Washington.
Mm-hmm.
And the red dots are dated Eocene plutons. And the story was that they get progressively younger as you go to the southwest. And the model was that the slab has broken off and begun to roll back. So there's a couple of immediately obvious similarities between what's happening here and the slab failure story. The first one is that all of this is happening quite promptly after a terrain accretion event,
Yes.
which I think, for which the evidence I think is pretty good that that's terrain accretion event caused the slab to break off.
Okay, I have to say this. Like, I worked with the Dream Team for the last 5 years. Bob Miller, Stacia Gordon, Mike Eddy. I think in the last episode of the Crazy Eocene, I kind of put everybody on the spot. It's like, okay, Eocene, are we all good that this can't be an arc story? And they're like, yep, that's right, Eocene, right. It's slab failure, it's whatever, but it's definitely not volcanic arc. They were unwilling, at least with me, to go older to 100 million years ago and use the same logic, even though there's a terrain accreting there as well. So to me, this feels like new. I don't even expect you to comment here, Jeff, necessarily, but this feels new to me that we're taking these relationships between terrain accretion and a bunch of magmatism inboard of that, and everybody feeling fine 50 million years ago, but quite a few folks being uncomfortable 100 million years ago, or even older than that. So that's why I'm into this. Like your work here in the Eocene, I'm just wondering if we can just go backwards in time and use some of the same logic. All right. I don't expect you to say anything.
Okay, I won't say very much except
Yeah.
to say that it's obviously easier to make the story when the rocks are younger.
Yeah.
So we have better handle on plate geometry,
Mm-hmm.
including what was subducted. So I think
Yes.
I'll stop there.
Right. That's good. It's good.
But the point I was going to make was that in terms of the big picture tectonic setting, it's about the same. There's a terrain accretion event followed by magmatism farther inboard than the normal arc.
And nobody's arguing back that anything on this map in the 52 to 44 is arc magmatism at this point, right?
I don't think so.
No. Okay.
I mean, it doesn't. There's no. All right. Then the other point I'd make here is that a lot of these rocks, these Eocene rocks, have this garnet in the source trace element signature.
Mm-hmm.
So this might be a little small, but plotted here are three age groups of rocks. There's the Eocene rocks in red.
Okay.
There are Cretaceous and Paleocene, so they're slightly older rocks in blue.
Okay.
And then there's data from modern Cascade granites in this lighter color. And maybe it's easier to see. So these plots on the side here are kind of density distribution plots.
Okay.
So here's our strontium yttrium ratio.
Yeah.
And when it's high, there's garnet. When it's low, there's plage. And so for the Cascades, everything is pretty much low. And that's what you'd expect in an arc.
Okay. Yeah.
For the older rocks, it's more spread out, but there are definitely a lot more red dots up here in this sort of
Yes.
eclogite field. And the same pattern shows up in our other um,
Huh.
trace element ratio, lanthanum, terbium. Again, when it's high, there's garnet. And so again, Cascades, no evidence for garnet. Melting must be shallower,
Huh.
like in a normal arc. But in the Eocene stuff, and to some extent the Paleocene stuff, ratio higher. So that the threshold's about 10. So a lot of this material, although it's not high on this plot, is above the garnet
Yes.
signature
Yes.
threshold.
Huh.
Okay, so those observations say this looks like a slab failure story.
Hmm.
But there are some other data that are different. So, and just to tell you where we're going, I'm going to say that what we're seeing here is melting in the crust, not melting of the slab.
Okay.
So one observation is that there are changes in isotope composition of strontium and neodymium, and those ratios, tend to be higher in older continental material than in the mantle.
Hmm.
So the point I want to make is that those isotope compositions cluster in geographically, and those clusters correspond to known mapped at the surface boundaries between terrains.
Mm-hmm.
So what I'm plotting on here is not really an isotope ratio. It's what's called the mantle age, depleted mantle age, model age. But these the open white circles, the gray circles, and the black circles have different isotope
Yeah.
compositions,
Nice.
but they correspond nicely to something we see in the crust.
They sure do.
Um, Second point is oxygen isotope compositions. And again, the mantle has a value about 6. Crust has something like 10.
Hmm.
And so these are the rocks in Northeast Washington. For comparison, these are Columbia River basalts. They look like mantle, but some of them have been contaminated with crustal material.
Hmm.
And as a result, their strontium ratio goes up, but and so does their oxygen.
Mm-hmm.
The point is, we never see anything that looks mantle-like in these Eastern Washington granites. They
Hmm.
all look like crust. There's no sign that this has a component of this mixed into it.
Hmm.
It's just a horizontal array.
Mm-hmm.
So that says these two things to me, the age pattern of isotopes and the oxygen isotopes say that we're melting the crust, we're not melting the slab.
Mm-hmm.
And then the last thing has to do with this garnet signature. These are the uh, analyses of samples over time from 120 to 40 million years ago. And the message here is that this ratio is increasing, which says the crust is thickening.
Hmm.
And so, and that both of these trace element ratios show that this ratio is changing over time. And we know there was a big orogenic plateau
Yes.
forming in eastern Washington.
Yes.
And then we get to the beginning of this rollback story, and that orogenic plateau collapses. And
Collapses.
these, but the point I want to make here is that you can have an eclogite signature if the crust is thick enough. You can
Mm-hmm.
melt the crust and get it. And
Hmm.
that's why I think it's knowing that garnet was in the source doesn't automatically require it to be the melting of the slab.
Hmm.
It could also be the thick crust, but you'd have to have some evidence to tell you which is which.
I
So I
see.
think for Northeast Washington, the crustal signature of the oxygen, the correlation with crustal terrains, and the evidence that the crust was thick enough to have garnet at the base all say that here it's not exactly the same kind of slab melting story as Bob is proposing.
Okay. Hmm. Interesting.
Why it's different, I thought about this, and maybe Bob will comment, but I think one thing that might be different is that this was a flat slab. And so, unlike a normal arc where it breaks off and you've got something sort of hanging vertically and then melting and maybe just having a relatively narrow zone of failure magnetism, this
Mm-hmm.
was out of, gravitational equilibrium. So it's doing something like this.
Mm-hmm.
which is causing a lot of upwelling of the mantle and then melting of the crust.
Mm. Mm.
So anyway,
Okay, thank
that's a
you.
lot to absorb. All I would say is that I think this is a variation of magmatism associated with something slab break off like,
Yes.
but in this case, you're not melting the slab, you're melting the crust.
Okay. Okay.
Okay, can I do one more here?
Absolutely.
I just wanted to say something about this this suite of rocks that has been very influential in the, excuse me. Uh, so in, I'm not used to lecturing.
You okay?
Yeah.
Okay.
Okay. So in Yosemite Valley,
Yeah.
in is the Tuolumne Suite, and it's this set of plutons that are sort of nested. So they're shown here in these different colors. Um, but they were emplaced sequentially one after another. So there's the Half Dome, the Cathedral Peak, um, Kuna Crest,
Mm-hmm.
and they're just magnificent. And so they've attracted a lot of attention over time. Well, how do we make this series of magmas that intruded in the same place one after another and are similar but not the same?
Mm-hmm.
So if you plot data from those, they define this nice linear array. So this is just calcium and silicon. So when this was, first studied in late 1970s, the model was, okay, these are related by fractional crystallization. This is Bowen's influence,
Yes.
90 years later or something.
Right.
Well, not 90, 80, 60. But anyway, um, then subsequently there was an isotopic study, and it showed that these don't all have the same isotope compositions.
Yes.
And you can't change an isotope composition by fractional crystallization. So
Okay.
that meant, well, maybe this is a magma mixing
Uh-huh.
story.
Uh-huh.
Subsequently, these plutons were dated. Well, it turns out that they span something like, 5 million
I
years.
love this.
So they can't,
this is
this is so, I think this is so cool, but also so instructive of how,
yes.
as you learn new things, you have to incorporate the earlier data into a model that accounts for your new observations.
Right.
So they can't all be part of the same magma story really at all. So now they must be related to these. The differences are changes in the source,
Right.
unspecified.
Yes.
But the source is generating batches of magma one after another, millions of years apart. And then Bob comes along, and we didn't talk about these ratios, and I'm not going to define any new ratios. I'm just going to say that these ratios, again, say something about depth of melting.
Mm-hmm.
So this one on the bottom is the same as lanthanum ytterbium. It's just
Okay.
another garnet. This one's based on some experimental work. But the takeaway from here is that the older stuff is shallower than the younger stuff. So
Mm.
now we not only can say something about the source is changing, but the depth of the source is changing. So I don't know what data might come after this, but this is how, geology and petrology moves forward with new observations, new models, and new interpretations.
That's a great way to end. If you can stop your share, I've got three final thoughts.
Okay.
First one is thanks. It's great to have you back. You're a well-known guest by now, and you're a loved guest because you're always careful. You have detail, but you're also kind of open to, you're open, and not everybody's open. So thank you for that. Number two, we're both over 60. So we've seen some of these changes just as, in my case, a spectator and you a participant in the research over the course of 30 plus years. And so as you get older, you realize that whatever you're hearing right now is it's probably incorrect to say it's the fashion of the day, but there's kind of an element of that it's not a permanent thing. Of course, we know this in science, that we just keep evolving with the thinking as the data continues to come in, if you're open to all the data. I think the third and final thing I want to say is that I've lost track of how many people I'm talking to in geology about Hildebrand. And most everybody says, A, I don't know anything about Alaska. I'm not going to comment. I don't know anything about Mexico. I'm not going to comment. I don't know anything about any of these places, so I'm just lost. But B, the other thing that always comes up is all those geochemical discrimination plots, I don't know what to do with that, but they seem important, but you got to find somebody to try to translate some of that and see if Bob's really onto something or not. And that's what we're doing here today with your work. And so I may come back to you, Jeff. I don't know how much time you've got this winter, but as we
I'm retired.
as we
Remember?
continue to, I do remember that, yes. You got yoga in the morning, and then what are you, you're fixing your clocks the rest of the afternoon, so we're good.
So I have to be wound.
So you're a resource, and I don't know how much will come back to you, but I'm guessing that this kind of thing will keep coming up, and maybe you'd be willing to come back on in this format, and we'll do one or more of these.
It's an honor.
Okay.
It's an honor.
Thank you. Well, hold the line, please. I'm going to stop the recording. I think this one was more like an hour, but that's good. We took our time, and we got into where we wanted to go here today. And so please hold the line. We'll chat a little bit more. But
Will do.
thank you, Jeff Tepper, for your time today.
Thank you, Nick.